OK, so now we get into some more fun pictures here. So let's take a look at a processor based on the in-order processors we've been looking at up to this point. We have fetch, decode. We added or renamed some stage here, which we'll talk about in a second. And then we have different pipelines and one write back. We have two register files. We have a scalar register file, which is what we were calling our old register file. And we have the vector register file, which has lots and lots of data in it. The vector length register sort of sits out in front here in our register fetch stage. And we make a special stage for this because it does a lot of work. What is it going to do? Well, when an operation gets to this stage, it's going to start reading the register file. And if you have a vector register, it's going to sit there and read the first element, the second element, the third element in time, and start shoving it down one of the pipes. So let's say this is our multiply pipe here. It's 4 stages long. And we do a multiply of 60 with a vector length of 64. It's going to do 64 sequential reads out of here, and then send 64 instructions down this multiply pipe. Note, we are not looking at any parallelism yet in this example. We are doing everything sequentially here. One thing you will note is instructions can stop here, and they basically generate more work at that point, and up to the maximum vector length, or whatever the vector length register is currently set at. So let's look at a basic operation here. We're going to have a piece of code which is doing the same operation. We're taking vector A and vector B and element-wise multiplying them. And I is 4. I use a small I here because it's hard to draw these things with I of 64. There's just lots of instructions to draw. If we go look at the assembly code, it's the same assembly code we had before, but we load the vector length with 4 instead of 64. So load vector, multiply vector, vector, double, and store. Let's look at the second load, multiply, and store. I don't have the second load or the load immediate on here because it just took up too much space. This load vector here, it's going to start off, it's going to fetch, decode, and then it's basically going to sit at the R stage for a while, inserting loads down the pipeline. OK. This basic vector execution, we don't have any bypassing, and we do register dependency checking on through the register file and on a whole register. So we stall an instruction if the whole vector is not ready. Now, we're going to look at ways to make that better in a second. But what that means is we wait for all of the values of this load to write back to the register file before we go and start to do the register fetches of the next instruction. Then we do the multiplies. The multiplies have longer pipeline lengths. We wait for all of those multiplies to write to the register file before we start to go do the stores operations. So our scoreboarding here is very, our scoreboarding and our bypassing here are very limited. You can have basically check to make sure everything is in the register file before you go ahead. I did want to introduce one piece of nomenclature. And your book calls this out. It's called a chime. So a chime is how long it takes to execute one vector instruction on the architecture. So what we're going to see in a little bit is we're going to have some architectures where you can actually overlap some portion of the execution, let's say by having different functional units, and decrease the chime. So for this architecture here, the chime is 4, because it takes basically occupancy of 4 vector length of 4. And we only have one ALU effectively that can be used at a time here. So now let's take a look at how to how to make things run a little bit faster. We exploited no parallelism. The only real advantage we've taken advantage of here is we've decreased our memory bandwidth. We've not actually, or decreased our instruction fetch memory bandwidth. But that's not a real great reason to go do anything. It probably reduces power a little bit. But we wouldn't go fast. So we can start to think about how to overlap if we have different functional units, x0, the load, or the ALU, the load, the store, and the multiply unit, we can start to think about overlapping them in both space and time. So here's an example where we're executing 32 elements is our vector length. And we actually have multiple copies of the functional units. And we have multiple function units. So we can overlap different executions with each other. And we'll look at some more detailed examples in a second. So we can start to add parallelism by using multiple units at the same time. Our adder unit, our multiply unit, our load unit, this was L, and this was our Y, and this was our X units. And we can actually put multiple copies of those. And we're going to call those lanes.